Let's start by going to the process that we went through yesterday. So here we've got a set of data that we think has a correlation. And what I want us to do first, even though it doesn't say in the question, is to confirm that by calculating R. Alright, so let's get our calculator into stats mode, and you enter it into the correct columns. So this will be the first column, this will be the second column. Actually, it doesn't matter which way around. R, it doesn't matter. And R is going to tell us to what extent those points line up. So it tells us to what extent those points line up. So we're measuring linear correlation. So it's stats mode, just enter it as two-column data.
So, if I could give something and it says put thousands, and it said 5 but in the thousands, would you type in 5,000?
I would type in 5. Yeah, I would type in 5. And I just remember that any answer I got that was a value of H would be in thousands. But no, you don't need to, you can do the actual values. So you get an awful lot of stuff that you don't need, but the key value is the value of R. And then go on and answer the rest of the question. If you're ahead of them. Just a reminder that right, I think, yeah, okay, I think there's a problem which Stasha noticed in the other group. Could you all check this for me? So I've got my raw data there. I'm going to go to calc. Before I hit reg, which stands for regression, I'm going to go to set. Now, for it to work, you need to have, for two variable data, you need to have X list for list 1 and Y list for list 2. Now, have you not got? Yeah, that's what I did. Right, so it's worth just, now that is the default setting, but Stasha found in the other group that that wasn't what she had, and she wasn't therefore getting the value of R. Now, if you've got that, it doesn't matter what you've got here, here, or here, it's just these two that need to be set up like that.
What happens if they're the other way around? You have to write the values the other way around.
Doesn't matter. For R, for the calculation of R, it doesn't matter. So then once we've done that, we go to reg, X, and it doesn't actually matter, but A plus BX is the one we're doing. And R of 0.83, that's a really strong positive correlation, so I feel comfortable to carry on with the rest of the question. Yes, you certainly can. So see if you can finish off with that R value. Are we all okay with that? See if you can answer the rest of the question while I go and get Lily a new book.
Can I use it, please?
Yes.
Thank you.
This is in the new book?
This is actually in a different book. So yeah, but the rest of today will be from the book too. So.
No.
So then explanatory yes.
And I went to Buckingham Palace there, like, or something like that.
So the first thing I always think is important to get your head round are what are the variables. So in this case, I've got h, which is my x, and b, which is my y. So I'm hoping my regression line is going to say b equals, because that means it's the y on x regression line that I can use to predict y. And yes, it is. That's good. And h is the x, which is there. So that means that this is my gradient, and this is my y-intercept. George, even if I hadn't worked out r, how could I have told from this line that it was a positive correlation?
Because well, actually, the one before H is positive.
Yeah, positive gradient. That's right. Yeah. So we've got that double sort of confirmation, haven't we? That we've got a positive correlation because the gradient of this line is 429.5. So interpret the value. So so Charlie, what does a gradient of 429.5 tell us in this graph? Say again, sorry? Yeah, I think perhaps more important than that, it's the effect of increasing the number of hours on sales, isn't it? So if you spend more hours, your sales are going to go up. So this is the expected increase in sales for every hour you spend designing the colour. Slightly odd example, but there we go. And then use the regression line to predict the value of the book said 6 hours. And let's just check that's the right way round. Yep, we are using x to predict y, so that's the way that this is supposed to be used. So what we do is we just make x, or h, sorry, equal to 6. So I get I get 2,951.7. Beth, is that a reliable estimate?
What was the number, sorry?
6 hours.
Is it not because it's not?
It's not that it's not up there, but it's okay because it's within the range of value. So we've got hours from 2 up to 15, so 6 is slap bang, so that's okay. So that's a reliable estimate. The other reason it's a reliable estimate is that we've got strong correlation. So at the weaker the correlation, the less reliable the estimates are, because these points will be further away from the line of best fit. And the last, sorry, I didn't mention it. So the explanatory variable, that's the independent variable, the x variable, so that's number of hours, and response variable, that's the thing that is being affected, that's the sales, that's B. Okay, now that all seems pretty straightforward, doesn't it? You get a set of data, we don't even have to plot a scatter diagram anymore, we've got a way of measuring correlation, which is beyond the way we used to do, where we used to look and say, yeah, that's a pretty strong correlation. And we're not even being made to calculate the line of best fit, we are told the line of best fit. So, so where's the complication? Well, I did promise you it was easy street, but I'm afraid it does get a little bit more complicated. Because not everything has a linear relationship. Not everything lines up when you plot it on a graph. There are some things which are non-linear, and we've come across one very big example of a non-linear relationship, and that's exponential growth or decay. That's where you have two things which are definitely not related by a straight line, they're related by the classic exponential growth or decay line. Can we still use correlation in situations like that? Well, we can. So we're going to talk about linear correlation, which is what this is, straight line correlation, in non-linear situations.
It just sounds very contradictory.
Absolutely, isn't it? It's quite neat. It's quite neat.
I think so.
So let's talk about exponential growth as the first example of this. So, e.g., exponential growth. So exponential growth, we know, is related, and the letters vary, but something like this. If we're dealing with x and y, and x actually with exponential growth is nearly always time, isn't it? Nearly always time. And y is often the number of things, either growing or decaying. We know that this is our initial value when x or whatever is 0. So that's the initial value. And this is our multiplier, what we're multiplying each time. And Harry, what am I looking for in the multiplier to tell me whether we're dealing with growth or decay? It's not positive. Think about
that
what
would just be if it's above 1.
Yeah, above 1 is growth, and between 0 and 1 is decay. Exponential things don't tend to grow with a negative multiplier because they sort of flip-flop between positive and negative. So, yeah. So you know, let's say in this case that b is bigger than 1. So you know we've got that sort of classic shape. Now that is not a straight line. So if we worked out r for that set of data, whatever that data is, it wouldn't give you an accurate measure of how exponential it is, because r is measuring linear, straight line correlation. So what can we do? Well, it's quite a neat trick. What we do is this. We say, and we have done this at the end of last year without talking about scatter diagrams. So what we do is we take our equation and we log both sides. Now I could use logs to any base. I'm going to use log logs, that's log to the base 10, which meant we don't bother writing the 10. So I'm going to log both sides. So I've logged that, and I've logged that as one thing. Now on the right-hand side, I've got k multiplied by b to the power of x. I can use the first log rule to split that up, because I know that log a plus log b is the same as the log of a times b. So I can use that rule in reverse to write that. And then I can use the third log rule. The third log rule to do that. Now let's now compare that with the equation of a regression line on a graph where the variables are y and x. Well, it's sort of the same, isn't it? I've got b times x, and in this case I've got log b times x. And I've got a constant term a. Well, the log of k will be a constant term because k is a constant term. The only difference is, instead of y, I've got log y. So what that means is, if you take an exponential relationship and you plot it on a graph where on this axis you have the log of the y value, so instead of plotting your y values, you plot the log of the y values, you get a straight line. A straight line with this equation here. This value here is the log of k. And if I know what the log of k is, I've got a way of unlogging things. I know that to undo log logs, I just do 10 to the power of. And I know that the gradient will be log b. And if I know what the gradient is, I know what log b is, then I can 10 to the power of to work out what b is. So I can get back to my original equation. So this is a really neat trick, because sometimes you think something's growing exponentially and you want to describe it with a with a formula, but you don't know how to do it, you can use this trick to do it. Now, how do I remember that if you've got exponential relationship, you have to log the y-axis, and the intercept is the log of k, and the gradient is the log of b? I have no idea how you'd remember that, but I've just worked it out by starting with that formula, and in these questions you'll nearly always be given that formula and going through this process. And going through that process reminded me that my variables should be log y and x, the intercept is log k, and the gradient is log b. So, shall we do an example of this? Let's, and we'll find it in this book, and it's about moles. It's at the bottom of page 3, and I don't mean the chemistry moles. I mean the little plant. Actually, no, sorry. I think it's it's page 3, question 4. Page 3, question 4. So, moles are doing what moles do, and their population is growing. And what I've done is I've plotted that data as it is. So here's the data as it is in Desmos. And it looks like a classic exponential growth, doesn't it? It looks like classic exponential growth. So I said, oh, that's interesting. Okay, it's classic exponential growth. So let's plot it where this axis is the log of y. So I've got x against the log of y, and look what happened. I've got a straight line. So I'd like you, just for this one example, I'd like you to do this for me, to plot this graph. So here's what we're going to do. We're going to set up a set of axes that go from 1.5 to 2.5 on the y-axis. The x-axis is just going to go from 0 to 10. And I want you to plot, sorry. I lost it. Oh, so I want you to plot, sorry, and it's t, isn't it? So we've got t, and this is going to be the log of p. So I want you to plot this value, 2, and the log of 7.2. Sorry, the log of 72. So you're just going to type log 72 and plot that point there. And you're going to plot 3 and log 86. I promise you this is the only scatter diagram I'm going to ask you to plot as part of this topic. All right? I think it's worth just seeing how when you take a set of data which is exponential, this is not a straight line, this is exponential, and you log the y-axis, you get a straight line. And what I'd like you to do is to tell me the y-intercept and the gradient, so calculate the gradient and the y-intercept for me. So your x-axis is going to be t, and that's just going to be normal. So you're not logging t, the only thing you're doing is logging, and you're using log logs, not ln, but log logs, which is log to the base 10. So what power of 10 is 72? It's going to be almost 2, because log of 100 is 2. once you've plotted your graph, I'm hoping you're going to estimate the gradient and the y-intercept. Amber, come on, you're supposed to be right outside. So it doesn't matter if you don't get the same as me. We're only estimating, and I've been very rough and ready with mine. So I extended the line, found where it crossed the y-axis. Obviously, that has to be the value where we get to 0, so it had to be 0, and I got my gradient here worked out. So if I go back to the original question, and we flip over the page, we find, which, as is often the case, they're telling us the relationship. So they are suggesting that it is an exponential relationship, and often that's hidden later in the question. So I've got A is the initial value, which I'm trying to find. B is the multiplier, which I'm trying to find, and P and T are the variables. So I'm going to find that in the question, and it's nearly always later in the question because I'm just not very good at the whole which axis is logged and what are the two things, the intercept and the gradient, what do they mean? So every time I do a question like this, I'm going to go through that process we went through a moment ago. Different letters this time, but it's still exponential growth. I'm going to do the next two steps in one go. So that reminds me that I need to have a graph with log of P and T, because they were my variables, and in this equation, T is still T, but P's become the log of P, which we've got. We've done that, tick. So log of A is the y-intercept. So I got 1.7. So to unlog, you do 10 to the power of. So A is 10 to the power of 1.7. Log log is log to the base 10. So I need to do 10 to the power of 1.7. And that's going to give me my initial value, which in this case is the number of moles at the start of this particular thing. And there's a 10 to the power of button above log. Don't have to use it, but if you do shift log, you can do 10 to the power of. So that's 50.1. So there were 50 moles to start with. The gradient is always the coefficient of x, or in this case t, so that's log of b, and b, don't forget, is the multiplier. And actually, I really perhaps ought to use the exact value there. There's no reason why I can't. It was 0.7 divided by 9, wasn't it? Yeah. So I'm going to do 10 to the power of that. So that gives me 1.196, I'll say 1.20. So that's the multiplier, isn't it? That's the multiplier. Every, what were the units? I've forgotten. Every month, so every month the number of moles gets multiplied by 1.2. We started with 50 moles, and then they get multiplied by 1.2 every month. We've modelled this situation. We didn't know it was exponential, but we have tried to see if it is by logging one axis. We've got a nice straight line. So we can therefore say, going back up here, that the number of moles is equal to 50.1 times 1.2 to the t. Yes?
How did you find the intercept?
I just did it from the graph. So I just joined my points up and just said, where did it cross the y-axis? The only thing to remember, though, actually in exam questions, you'll be given the equation of the line of best fit. So we'll do one of those in just a minute. So I tell you what, let's go back to my Desmos graph. The original one where it was. Here we are. So if I plot the equation we've just worked it out to be, so I've just worked out that it's 50.1 times, what am I doing there? 50.1 times 1.2 to the power of 2. 1, 2 to the power of t or x, I'm doing it. It's pretty close. Yeah, so those points we've used the equation that we've worked out, and yeah, it matches the points really, really well. And this is a really useful technique where you've got a set of data that you think is exponential, of A, testing that it's exponential, and then B, finding an equation for that growth. And you know, and all around the world at the moment, this is what people are doing, looking nervously at case numbers, trying to model what's going to happen, and making sure they've got enough lateral flow tests, making sure they've got enough hospital beds and all those sorts of things. So,
Well, lateral flows aren't even they're even accurate.
well, better than that, isn't it? Better than that. Right, let's do another example of this, which throws in the calculation of R. Because don't forget, we mustn't do this unless we've calculated R. So can you jump to page 7 in the textbook?
7's one of my favourite numbers.
And question 4.
I won on things that way.
So question 4. Now, in this question, it's not immediately clear to me whether they think this is an exponential growth or not. I mean, it's a fairly obvious application of exponential growth. It's decay, it's radioactive decay. But it's not until right at the end of the question that they throw it in there. But the first thing I'm going to do is I'm going to start with that, and I'm going to go through this process just to remind myself when I do come to look at the graph of this, what the different things are going to do. So can I encourage you to do the same? Start with n equals a, b, t. Look at the question and say, right, there's 4 letters there. What are the variables? And then what are the other 2 letters going to tell me? Go through the process I went through there. It's identical, just with different letters. So just remind yourselves what the variables are and what the other letters will actually tell us. So it's page 7, question 4. So n and t are my variables. So I look for those at the end here, and t is still t, but n has become log n. So that reminds me that if we were to do a scatter diagram, we'd have to log the n axis. And if I get a line of best fit, I'm predicting it's going to be downhill, but I might be wrong. The intercept is going to be the log of A, and the gradient will be the log of B. But firstly, in this question, we're not going to copy and complete the table, because the first thing after that they ask us to do is to calculate the product moment correlation coefficient, because we might be wrong. There might not be an exponential relationship here at all. So let's use product moment to confirm it. That's the clever way of plotting a scatter diagram. We don't want to plot a scatter diagram because it takes a long time. Now be clear, if I do product moment for that data, I won't get a good value of R because it's not a straight line. It's exponential growth or decay. It's either that or that. So what I do is I compare T with log of N. And the great news is that you can type that in on your calculator without actually having to work out the log yourself. So you can type 1, 2, 4, 5 and 7 in your first column, and in your second column it will let you type in log 231. Log 41, log 17. So rather than copying and completing the table, let's let our calculator do the work. Let's get our calculator to tell us. And if you want to delete on the first page, pressing the delete F6 takes you to delete, and then you can delete everything. That saves you having to do it a column at a time.
That's not a nice spot.
Do you not get that?
Wait, no, I think I did something wrong. Didn't
So those are the values you should have. Sure you haven't got any spurious values at the bottom? But yeah, there. So I was right. It's a downhill line, and it's a really, really, really strong positive correlation.
Yeah.
And so what that tells us, if this graph lines up really well, it means the original data must be exponential. So we've confirmed that it's exponential. So go on, bring the rest of the question home. Just see if you can calculate the values of A and B, and therefore get an equation for this growth stroke decay. And the good news is we haven't got to worry about drawing the graph because they give us the equation of the regression line, so we can straight away see the intercept, we can straight away see the gradient.
So what would I actually write for C?
For C, with reference to your answer, a graph of t against log n has a strong negative correlation, which means an exponential model is a good fit. Yeah, I'm pleased you've made that point actually. Yeah, so because a graph of t against log n had a strong linear correlation, negative in this case, an exponential model is a good fit for the data. It's interesting, isn't it? Data is plural. Datum is the singular.
Datum?
Yeah.
This just sounds so weird. Datum. I have
So
one.
data is plural, so you have to say these data rather than this data.
What? Nah, I'm going to say these data.
I know, it sounds a bit odd, doesn't it? I bet if you go to university and do maths, you'll be forced to. So, no need to draw a graph, because we're given the line, as we always will be. So what's the intercept on that line, Beth?
That's the 2 point.
Yeah, that's right. So I'll let you carry on.
It's certainly easier than Shrek. Oh, there it is. Very necessary.
So we found an equation, and we can interpret those values. 307 was the number of atoms to start with. And every, what's the time period again? Every minute, it's pretty much halving, isn't it? Our multiplier is 0.479, so every minute it's halving. And again, how do I remember what the intercept and the gradient actually tell me? How do I remember that that's what they tell me? I don't. I mean, it's just too much to learn, isn't there? So what I do, every question I do like this, I find hidden in the question what they think the relationship is, and I do the whole log thing, and I use that to to start with, and that helps me answer the rest of the question. So we calculated product moment, which just confirmed we were okay going for a linear model, which meant that in this case, because it was t against log n, the original data was exponential. That saves having to draw the scatter diagram, particularly as they then go on and give you the regression line equation and Bob's your uncle. And actually these values here are on your calculator when you do the calculation of R. So you get A and B. You don't need to get them, but they're there for you as well. Okay, so that's the first of two nonlinear situations that we need to come across. Exponential growth or decay. There's one more. First of two, so there's only two. So the other one is, and this tends to occur in science a lot, where you get two things which are related by a power. So pendulum experiments, I never forget if it's squared or square rooted, but as the pendulum gets longer, the time that it swings, I think it's related to the square root of the length. Anyway, so there's lots of things in science which are related by a power, not exponentially. So they are, so this is, I call this sort of a power relationship. So this is where you've got two things that are related like this. So the variables are y and x. The power is not the variable this time. In exponential growth, the x or the t is in the power, but here the variables are here. N is a constant, a is a constant. And these graphs, well, they'll look like that if n is a number bigger than 1. So, you know, x squared, x cubed, obviously x cubed is negative down here, but in this quadrant it's positive. X to the power of 4 is just a bit flatter bottomed, but still that sort of shape. And if it's a power between 0 and 1, like for example the square root of x, you get this sort of relationship. And how can you spot the difference between this and exponential growth? Well, this will start at 0. When x is 0, this is 0, whereas exponential growth will start at 1 for the basic a to the x, or at its initial value if it's multiplied. So let's see what happens when, and obviously, so if we've got data related like this, linear correlation doesn't work. But let's do the whole log trick again. I'm going to do the two steps separately this time. Now look what happens this time. Remember, my variables are y and x. Look what happens when I've gone through the log process. I've now got log of y and log of x. If I want to test for a power relationship using linear correlation, I need to log both variables. And that will give me, if it is a power relationship, a straight line. It will give me a straight line where the intercept with the axis is the log of A. A was this multiplier that was accelerating the power growth, so that's the log of A. And the gradient is just n. So actually the gradient we don't need to do anything to. That's just going to be the power in our power relationship.
Log of A. Can you just write log of A?
Yes. So that's the intercept, isn't it?
Okay.
Yeah. Sorry. I should have said gradient. Intercept should be, sorry. I should have said. So back on page 3, I know we're jumping around a bit, back on page 3 we've got a question which uses this sort of relationship. How can I tell that this question is one that's about a power relationship rather than exponential growth? Well, it's buried in the question. Look, all the way through the question we get to here. Y equals ax to the n. That's not exponential growth because x, the variable, is not the power, it's there. So this is a power relationship. This is one of these. So all I need to do is to work out the intercept and the gradient from that graph. They've logged, look, they've done it a slightly odd way. They've called the log of x big X and the log of y big Y. So what we've basically got is this is the log of x and this is the log of y. They've logged both axes. And we've got a pretty good correlation. It's not super good, but that suggests that we've got this sort of power relationship. So go on. The intercept is obvious. Use the bishop to work out the gradient, and then see if you can get me an equation like this. Obviously we've got a downhill one this time, not an uphill one. So forgive me for not working out 10 to the power of 172. I haven't got enough time to write all the zeros. But it's a big number. And
90.
63 over 23 isn't a very nice number either, so I'm going to do 3 sig figs for that, so that's 2.74. So in this case, the gradient is n, which is the power. So y is equal to 10 to the power of 172 times x to the power of 2.74. So that's going to be a graph that goes through 0, 0, because when x is 0, 0 to any power is 0, but it's going to go massively steeply up because you're multiplying by a huge number. So, again, how did I know that this was the case? No idea. I just derive it every time. Doesn't take me long. I derive it every time. I find what they think the relationship is, which is often buried in the question. I do the log trick, and we're off to the races. This is perfect timing. We'll do another couple of examples next lesson, and there's. Oh, sorry. Yes. Thank you. Thank you, Grace. There you go. What would I do without you? Yeah, and tomorrow we've got one more bit of this to do, and we'll all be done. And well, no, bit of extra practice next week.